This video is part 2 of the definition and elements of communication systems. Waveform representations. We can represent the signal in the time domain. There are two examples of sinusoidal waveform. In the left side, there is one cycle of the waveform. There is a positive and negative alteration. One wavelength is measured between two peaks of a waveform, or between any two similar points of the waveform. In this representation, amplitude is measured against time. To view the time domain representation, an oscilloscope is used. Here are the parameters of a waveform. The frequency is the number of full cycles per second. Period is the time it takes for one cycle to complete. It is the reciprocal of frequency. Amplitude is the vertical level of the signal waveform. These are the relationship of wavelength, frequency, and period of a given waveform. First, the wavelength is lambda. It is measured in meters. It is equivalent to the speed of light. In here, it is the variable c divided by the waveform's frequency. It is denoted by f. And then if we want to compute for frequency, it is equivalent to the speed of light divided by the wavelength in meters. And lastly, to compute for the period in seconds, we just have to get the reciprocal of frequency. Aside from the time domain representation of a signal, there is also the frequency domain representation. One example of the frequency domain representation is the Bode plot. In a Bode plot, the frequency is plotted in the x-axis in logarithmic form, and the vertical axis is the gain of the system in decibels. The importance of this is that we can visualize the gain of the system with respect to different frequencies. Another way of visualizing the frequency content of a given signal or system is a display from a spectrum analyzer. The spectrum analyzer displays the power in the vertical axis versus the frequency in the x-axis. In this example, we have 60 Hz, 120 Hz, and 180 Hz with their corresponding power level. Electromagnetic frequency spectrum. Based on the ITU band designations, these are the classifications of the frequency of the electromagnetic spectrum. First, on the lowest side, we have the extremely low frequency. Next, we have the voice frequency. This is the frequency of human voice from 0.3 kHz up to 3 kHz. Next, we have the very low frequency. After that, we have the low frequency. Next, we have the medium frequency. Next, the high frequency. And then the very high frequency. Next is the ultra high frequency. Next is the super high frequency. And then the extremely high frequency. After that, we are in the infrared. There are 3 bands for the infrared. After the infrared, we have the visible light. Next is the ultraviolet light. And then the X-rays, the gamma rays, and lastly, we have the cosmic rays. For extremely low frequency, we have AC power, low frequency telemetry signal, communication with submerged submarine, detection of buried metal objects. For voice frequency, we have human speech, telephone audio range. For very low frequency, there is the government and military navigation systems and sonar. For low frequency, we have marine and aeronautical navigation and radio beacon. For medium frequency, we have commercial AM radio broadcasting. It ranges from 535 kHz up until 1605 kHz. And then the maritime radio. Next is the direction finding. For high frequency, we have facsimile, shortwave radio, amateur radio, and citizens band radio. For very high frequency, we have mobile radio, air traffic control, police communication, marine and aeronautical communications, commercial FM broadcasting, FM broadcasting ranges from 88 MHz up until 108 MHz. And then commercial TV broadcasting, channels 2 to 13. Channels 2 to 13 ranges from 54 MHz until 216 MHz. After that, we have the ultra-high frequency. Ultra-high frequency consists of the commercial TV broadcasting channels 14 to 69, land mobile communication services, cellular telephones, radar and navigation systems, microwave and satellite communication systems. Next, we have the super high frequency. Super high frequency consists of radar and navigation systems, microwave and satellite communication systems. For extremely high frequency, we have radar and space exploration. For infrared, there is the heat-seeking guidance systems, optical wireless communications, night vision, electronic photography, astronomy, TV remote control unit. And then for visible light, of course, we have the optical fiber systems, optical wireless communications. Next, the ultraviolet. It is used for sterilization, suntan, detecting forged banknotes, and medical applications. For X-rays, it is used for medical diagnosis, and for gamma rays, it is used in food irradiation and cancer therapy. Bandwidth and information capacity. Bandwidth. Bandwidth is a portion of the electromagnetic spectrum occupied by a signal. The bandwidth of an information signal is simply the difference between the highest and lowest frequencies contained in the information. The bandwidth of a communication channel is the difference between the highest and lowest frequencies that the channel will allow to pass. More room at the top. Today, virtually the entire frequency spectrum between approximately 30 kHz and 300 MHz has been used. There is tremendous competition for these frequencies between companies, individuals, and government services in individual carriers and between the different nations of the world. The electromagnetic spectrum is one of our most precious natural resources. Communications engineering is devoted to making the best use of the finite spectrum. Great effort goes into developing communication techniques that minimize the bandwidth required to transmit given information and thus conserve the spectrum space. This provides more room for additional communication channels and gives other services or users an opportunity to take advantage of it. Spectrum management and standards. Provided by agencies set up by United States and other countries to control spectrum use. The Federal Communications Commission, or FCC, and the National Telecommunications and Information Administration, or the NTIA, are two agencies that deal in spectrum management. In the Philippines, the National Telecommunications Commission, or NTC, is a government agency tasked to manage the spectrum. Information theory. Information theory is a highly theoretical study of the efficient use of bandwidth to propagate information through the electronic communication systems. This can be used to determine the information capacity of a data communication system. Information capacity is a measure of how much information can be transferred through a communication system in a given period of time. It represents the number of independent symbols that can be carried through a system in a given unit of time. Hartley's Law. Developed by Ralph Vinton Lyon Hartley of Bell Labs in 1928, Hartley's Law states that the info capacity is directly proportional to the bandwidth in hertz and the transmission time in seconds. Shannon limit for information capacity. This is published in Bell System Technical Journal in 1948 by Claude E. Shannon of Bell Lab, relating information capacity of a communication channel to bandwidth and signal-to-noise ratio. The higher the signal-to-noise ratio, the better the performance and the higher the information capacity. Shannon limit for information capacity. It is given by this equation. Information capacity in bits per second is equal to bandwidth in hertz times the logarithmic base 2 of the quantity 1 plus signal-to-noise ratio power. This is a unitless quantity. Transmission facilities. Transmission facilities, in terms of bandwidth and in contemporary digital context, transmission facilities can be categorized as follows: narrowband, wideband, and broadband. Narrowband. Narrowband is a single channel, 64 kilobits per second, or some number of 64 kilobits per second channel, but less than wideband. Wideband. Wideband is a multi-channel capacity that is between 1.54 megabits per second and 45 megabits per second, according to US standards. Broadband. Multi-channel capacity which is 45 megabits per second according to the US standards and 34 megabits per second according to European and international standards. Transmission impairments. Signals travel through transmission media which are not perfect. The signal at the beginning of the medium is not the same as the signal at the end of the medium. Causes of these impairments are attenuation, distortion, and noise. Attenuation is when the signal loses strength due to the resistance and length of the transmission medium. Distortion is the alteration of information in which the original proportions are changed, resulting from a defect in communication system, usually in the channel. Noise is an outside source, such as crosstalk, that corrupts a signal. Circuit arrangements. Two-wire transmission, as the name implies, involves two wires, one for the signal and the other for a reference or ground, or a circuit configuration that is equivalent to only two wires. Under the two-wire transmission, there are two types. First is the passive two-wire transmission, which just consists of two wires as a channel for the electric signal to pass through from the transmitter to the receiver. One wire is where the signal travels, and the other is just the reference wire. The other is the active two-wire transmission, wherein an amplifier is added in the transmission line. This is usually done if the receiver is very far from the transmitter. Next circuit arrangement is the four-wire transmission. Four-wire transmission involves four wires, two for each direction, a signal, and a reference ground, or a circuit configuration that is equivalent to four wires. Four-wire transmission is ideally suited for full duplex transmission. This is an example of an active four-wire transmission setup. As you can see, both stations have a transmitter and receiver, so both can transmit and receive information. The amplifier in the middle is still used to compensate for any decrease in signal due to attenuation in the wires. When a two-wire circuit is connected to a four-wire circuit, as in long-distance telephone, an interface called a hybrid or terminating set is used to affect the interface. The hybrid set is used to match the impedances and provide isolation between the two directions of signal flow. This is an illustration of a hybrid circuit arrangement. As you can see, a hybrid set acts as the interface between the two wires and the four-wire lines. That's it for the basics.